Now we move on to discuss the applications of hyperconjugation. Hyperconjugation is having a lot many applications in organic chemistry, and the first application is stability of alkenes. We can use hyperconjugation to explain the stability of alkenes. Stability of alkenes and heat of hydrogenation. Enthalpy of hydrogenation or heat of hydrogenation. I will explain in detail. So, as you all know that when an alpha carbon with a alpha hydrogen is present along with a double bond, an alkene, so hyperconjugation is possible. So, let us consider this example. See, this is ethene, right? So, ethene. So, whether hyperconjugation is possible here? No, because there is no alpha carbon is there and alpha hydrogen is there. So, only double bond is there. No hyperconjugation is possible. So, similarly, when I will represent like this is also ethene, right? Carbon is there, so ethene. So, we can simply represent like this. So, alpha hydrogen is there, alpha carbon is there, 3 alpha hydrogens are there in this structure. So, in this case, what will CH3, CH3, 2 alpha carbon and 6 alpha hydrogen is there, right? CH3, CH3, and CH3. So there are 3 alpha carbon and 3 and 9 alpha hydrogen is there, right? And finally, CH3, 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 and CH3. So there are 4 alpha carbon and 12 alpha hydrogen. So which is more stable? We can define specifically as this last one, the carbon, the alkene which is carrying more number of alkyl group with alpha hydrogen atom possess high stability. So we can define it as stability increases with increase in the number of alpha hydrogen atom, right? Which in turn increases the number of hyperconjugative structures, right? Stability increases means number of alpha hydrogen atom is more here. So number of alpha hydrogen atom is more, which means number of hyperconjugative structure is also more, which in turn increases the stability of that compound. As a result of that, what is going to happen? Decreases the energy, the heat of hydrogenation. So stability of alkene will increases with the increase in the number of alpha hydrogen atom, and which in turn increases due to the increase in the number of hyperconjugative structure. So when an alkene is carrying no alkyl group, no alpha carbon atom, there is no hyperconjugative conjugation. So when one alkyl group which is carrying 3 hydrogen atom, 3 alpha carbon atom, so 3 canonical structures. Sorry, 3 plus 1 canonical structures are there. 3 plus 1 canonical structure is there. Here 6 plus 1 canonical structure is there. In this case, 3 alkyl groups are bonded, connected to the double bond. As a result of that, there are how many alpha carbon? 3 alpha carbon and 9 alpha hydrogen is there. Hence, the canonical structure is 10. And here it is 12 alpha hydrogen is there. Hence, this will experience as more stable. Okay. When the stability increases due to the increase in the number of alpha hydrogen atom, which increases the number of hyperconjugated structure. When a compound is having high stable, which means it is less energy. So least energy possessed by that particular compound. So hence the stability of an more stable the alkene is, less the heat of hydrogenation. What is heat of hydrogenation? It's nothing but when a double bond, the reduction of a double bond, the reduction of an unsaturated compound to a saturated compound in the presence of a metal. Usually, when hydrogen H2 reduction in the presence of nickel or palladium as the metal catalyst, this alkane will convert to palladium or nickel. Alkane will come to alkane. Means ethane will convert to ethane, which is called ketohydrogenation. The hydrogenation is the process of conversion of an alkane, an unsaturated compound to saturated compound in the presence of a metal catalyst by the addition of hydrogen. So the enthalpy, the heat generated is known as ketohydrogenation. So the stability, when more the hyperconjugation always decreases the heat of hydrogenation. This is the first application. The second application is stability of carbocation. Okay. Stability of carbocation. As you all know that when the number of hyperconjugated structure increases, the stability of that particular compound also increases. The same principle is applied to here. And the number of alpha hydrogen increases, the number of hyperconjugated structure, which also increases the stability. Also increases. Right? This is the principle behind all this. Okay, number of alpha hydrogen is more the number of hyperconjugated structure, more the stable is. Let's consider this example. CH3, CH2 plus or CH3 plus. Which is more stable? Yeah, we can say there is no alpha hydrogen. So there is no alpha hydrogen on the methyl carbocation. But in ethyl carbocation, there are 3 alpha hydrogen is there. So this is more stable. Ethyl carbocation is more stable than methyl carbocation. When we consider this series, this is a tertiary carbocation, this is a secondary carbocation, and this is primary or ethyl carbocation, this is methyl carbocation. Okay. So which possesses more stability? We can define with the support of this principle. When the number of alpha hydrogen is more the number of hyperconjugated structure, more stable is the carbocation. So here there are 3 alpha carbon atoms are there, and how many hydrogen atoms? Alpha hydrogen atoms. 9 alpha hydrogen atoms is there. 9 alpha hydrogen atom is there, and here 6 alpha hydrogen atom is there, and there's 3 alpha hydrogen atom is there. No alpha hydrogen. So we can say that more stable possess more alpha hydrogen atom. So tertiary carbocation is possess more stable than secondary, which in turn more stable than primary and methyl carbocation. Move on to the third application, stability of free radical. We can explain the same as we have discussed in the case of carbocation. So when the number of alpha hydrogen increases, conjugated structure also increases, stability also increases. So in the case of tertiary free radical, The number of alpha hydrogen atom is 9, and here it is secondary, which is 6 alpha hydrogen. In the case of primary, which is only 3 alpha hydrogen. For methyl free radical, there is no alpha hydrogen atom. So similarly, we can say that the order of stability of free radical is tertiary greater than secondary, greater than primary, greater than methyl free radical. Okay. We move on to the fourth application, dipole moment. Hyperconjugation always increases the dipole moment because hyperconjugation is a permanent effect which create a polarity in the compound which is permanent in nature. As a result of that, dipole moment increases. Let's consider this example. This is a formaldehyde. This is the functional group, aldehyde group, which is connected to only a hydrogen atom. Note, so no hyperconjugation. No hyperconjugation is here. So the dipole moment of formaldehyde is 2.3 dpi. Okay, this is the experimental result of dipole moment of formaldehyde due to the polarity, non-pair polarity of this aldehyde group. But when this functional group is connected to an alpha hydrogen carrying 3 alpha carbon carrying 3 alpha hydrogen atom, the dipole moment increases to 2.7 dpi. Do you know the reason why the sudden increase in the dipole moment when a methyl group is connected to this aldehyde? This is because of hyperconjugation. Due to the presence of 3 carbon hydrogen, alpha carbon hydrogen bond, this ethanol or acetaldehyde undergoes hyperconjugation or hyperconjugative structures. As a result of that, dipole moment increases. Fifth application of hyperconjugation is very important in experimental studies, that is abnormality in bond lengths of compound. So directly we will discuss with an example. In the case of an ethane, CH3 single bond CH3, this is ethane. Okay, the carbon-carbon bond length is 1.54 angstrom. Okay, and in the case of CH2 double bond CH2, this is ethene. In the case of ethene, the carbon-carbon bond length is 1.33 angstrom. That is the standard bond length of a double bond. And this is the standard bond length of a single bond, single carbon-carbon bond. When we consider the example of CH3, C double bond CH2. Okay, this is propene. Here, there is a possibility of hyperconjugation because alpha carbon is there, 3 alpha hydrogen is there. In these two cases, no hyperconjugation is possible. Okay. Here, hyperconjugation is possible. As a result of that, the carbon-carbon bond length, carbon-carbon single bond length will become 1.47 angstrom. That is, the carbon-carbon single bond length decreases. And what about double bond? The carbon-carbon double bond length will become 1.35 angstrom. It get increases. Okay, so we can define how this happens. This is because due to hyperconjugation, here hyperconjugation is there. Hyperconjugation is there. Because of hyperconjugation, this hydrogen, due to hyperconjugative structure, this hydrogen bond will comes here. The sigma bond will become shows a double bond character. The single bond will show a double bond character, and this double bond will show a single bond character due to hyperconjugation. As a result of that, the carbon-carbon single bond length decreases in propane and carbon-carbon double bond length increases in propane. Okay, this is the example, and we can find these kind of bond length differ abnormality. This abnormality through experimental, and we can utilize the concept of hyperconjugation to explain this abnormality in bond lengths. Sixth application is the reactivity, the ortho-para directing reactivity of toluene. So you know that toluene, this is toluene, right? So this is a benzene ring. So this is alpha carbon. So these are the three alpha hydrogen atoms, right? So the application is that toluene always direct the substituent to attack this ortho or this para positions. Here also one ortho is there. So ortho para directing property of toluene is due to hyperconjugation. What is the effect? We will show it is in resonance structure. Due to hyperconjugation, this will comes here. As a result of that, resonance will comes there, and a negative charge comes here. Double bond comes here. H plus H and H is okay. So resonance is always predominant than this, and there is also hyperconjugative structure is here, and this will continues. The hyperconjugative structure will continues in this manner. And this will comes here, right? And finally this will come here and this will come here. These are the hyperconjugative structures of a toluene. Similarly, resonance is possible in the aromatic group. Resonance is also possible. So as a result of that, due to this hyperconjugation on this alkyl substituent, this negative charge will comes here and this will comes here. So double bond comes here and negative charge comes here. Carbon carbon double bond with H H plus. This will comes here and this will comes here. This will comes here and this will comes here. Finally, C. Okay. So you can see that in hyperconjugation phenomena, due to the hyperconjugation property of this toluene, these alkane substituted aldenes, the ortho position, para position, and again the two ortho positions and para positions of toluene possess a negative charge, an electron cloud, a rich in electron cloud, which will facilitate electrophilic substitution. Electrophilic substitution reactions. So toluene always promote electrophilic substitution reaction to ortho para positions due to this hyperconjugation. Okay, this is very important.